Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Question 40 states that a neutral pion with rest energy of 135 MeV produced in a high-energy particle experiment moves at a speed of 0.78 c. After a very short time, it decays into two gamma-ray photons. One of the gamma-ray photons has an energy of 192 MeV. What is the energy of the second gamma-ray photons if we consider relativistic effects? So if we think of these types of reactions, one thing that must hold true is that we must have energy conservation. So the energy at the start, this rest energy of the pion, has to equal the sum of the energies of the two gamma ray photons. So the energy E on the left-hand side has to equal E1 plus E2. In this question, we're solving for E2. So we can just rearrange this to say E2 equals the total energy minus E1. E1 is given to us, and we have the rest energy of the pion, but because the question does ask to take into relativistic effects, we need to apply these effects to this E term. So I just bring this up here. E2 equals, the energy of our pion, mc squared, when we take into effect relativistic effects, 1 minus v squared over c squared, minus E1, again because E1 is known. So we can simply substitute in our values. The pion has rest energy, mc squared is equivalent to 135 MeV, divided by 1 minus 0.78 squared times c squared divided by c squared. That whole term is square rooted, of course, and we subtract off the gamma ray photon energy of the first photon, MeV, and we find our units for C cancel, of course, and applying this relativistic effects to three significant digits, because that's what's given to us, we find the energy of that second gamma ray photon is 23.7 MeV.